Hi, everyone. Welcome to the second part of our presentation. So in this part of the talk, you will learn about building a graph neural network using TensorFlow and TensorFlow-GNN. So my name is Neslihan Bulut. I'm a software engineer in TF-GNN team. Here's an overview of this talk. So firstly, I will go over the main graph structures in TF-GNN. Then we will take a deeper look at the graph tensors, followed by the message passing primitive operators available in TF-GNN library. And then we'll learn how to apply custom graph transformations. And finally, we will have a hands-on session building a GNN model with TF-GNN library using a Google Colab notebook. So TF-GNN library comes with native support for heterogeneous graphs, where you can have multiple entities and relation types. Edge level models where you can update edge states, GraphNet, and the NPNN model architectures. Tasks you can define at graph, edge, and node levels. Hypergraphs, which is a generalization of graphs that connect multiple vertices instead of just two nodes. So GNN models train over graph data, and in TF-GNN library, graph data is declared using a graph schema and represented as graph tensors. So graph schema is a protocol message to declare each node set and edge set, as well as their respective features, and the context, which is a graph level feature, and applies to the whole graph. Note that since TF-GNN support heterogeneous graphs, each different entity or relation can be represented as a separate node or as a separate node set or edge set. For example, in an academic paper citation network, each entity, such as an author, paper, or venue, can have their respective node set. Similarly, different edge sets, such as rights or sites, will have a separate declaration. You will define a graph schema once to build your GNN model. And graph tensor is the tensor format to store the actual tensor, actual data. And it's a composite tensor which holds the node sets, edge sets, and the context feature following the entity relations in the declared in the graph schema. And your features can be stored as dense tensors or as rugged variable sized tensors. So let's look at a concrete example how the graph schema and the graph tensor work together. And let's add this node set named user. A graph tensor can have multiple nodes of the user type. Here, graph schema declares the user node to have these name, age, and country features. Respectively, graph tensor will have the feature tensors for each of these features of the node set. Here, graph schema declares this is friend relation between the user node set, and we have the respective directed edges in the example graph tensor. So we can have different node sets, such as the item node set here, with price and category features. And graph tensor can have nodes of type item with the accompanying features. And the general guidance is to represent entities with same data under the same node set. For a purchased edge set between item and user nodes in the graph schema, graph tensor can have the actual nodes among these respective node sets. And note that here edge sets are directed. And if you need to represent an undirected graph, you can either add edges for the opposite direction as well into the same edge set, or declare another edge set with the reverse order of connections. Finally, you can also declare a context feature such as a scores here, which is a graph level feature, and it will respectively be present in the graph tensor. Context is a graph level feature and can be used for like graph regression or graph classification problems. An example from the chemistry molecule graphs will be like the boiling temperature of the molecule that you can use for your graph neural network model. So let's look at the graph tensor in more detail. It's a composite tensor similar to TF-Ragged and TF-sparse tensors, which helps for working with TF data and using them as input and output from your Keras layers. You will find three main pieces in the graph tensor, namely the node sets, edge sets, and the contacts. Each of these different pieces is called a graph piece, with fields to describe the feature information as well as the respective structural information. So let's look at a depiction of a graph tensor. Each node set graph piece has a dictionary of features keyed by the string feature name. And these features can be TF tensors or TF-Ragged tensors. So different node types will be a separate entry in the node sets graph piece dictionary. And you will use the node set name to key into the node set dictionary to access that node set. Here you can see the item node set with prices and category features. Category feature has a fixed dimension, accuracy node in the item node set, and represented as a dense tensor, while the prices feature has a variable length and will be represented as a TF-Ragged tensor. And each of these feature tensors will have their first dimension as the number of nodes in the respective node sets. So you can find for a specific nodes associated features in their features dictionary. Adsets graph piece is also a dictionary keyed by the adsat name. So different from the node sets representations, adsets have this adjacency structure that stores edge endpoints using the source and target tensors. These tensors keep the node IDs for the source and target nodes, and node IDs can be used as an index into the node set features tensor. The isFriend edge set here is a relation among the user's node set. So adjacency, source, and target tensors are indexes into the user's node set. For example, let's take as an example the first entry in the isFriend adjacency source tensor, which is a 1, right? This points to the first index 1, from the user's node set to the user with the username York. While the first entry in the target tensor, which is the endpoint, the endpoint, the target direction of that edge is 0. So this points to index 0 from the user's node set with name Sean. Different edge sets will be added as a separate entry into the edge sets dictionary, again keyed by the edge set name. And edge sets can also have features. So here you can see the purchase edge set has this feature named time. And this time feature of the edge set's first dimension is again the number of edges corresponding to each edge in the edge set, and that is the number of edges in this edge set is 4. So the first dimension of this time feature is going to be 4. In addition to edge sets and node sets, there is a context feature, which is used to represent graph-level information. So here you can see the scores feature, which could be used for a graph-level regression task. So we looked into the graph tensor details. How can you get a reference to a graph tensor? There is multiple ways. So one of them is you can create the graph tensor manually using the TF-GNN graph tensor from Pieces API, which normally you don't have to in practice. There is standard graph datasets that can be imported from the TF-GNN library. Specifically, the TF-GNN examples in-memory.datasets package has this standard graph datasets that you can import, access the respective graph tensor representations. You can also use our in-memory sampler and sample the graph tensors on the fly over these imported graph datasets. And while doing that, you can also get access to different representations of your graph tensor by subsampling them in memory. And we have a distributed sampler called the TF-GNN sampler, which can be used to create serialized TF examples that represent graph tensors. And you can also parse them to actual graph tensors using this TF-GNN parse single example API. And now that you have a reference to a graph tensor, how can you access the node-sat features and data-sat features, right? So let's take a look at some examples for that. So you can access the node-sats features by firstly using the node-sat name as a key into the node-sats dictionary, then using the actual feature name to access the feature tensor. Sat features can be retrieved similarly with a similar access pattern. First, you key into the AdStats graph piece with the AdStat name, and then use the actual feature name to access the feature tensor. And graph tensors are immutable structures like other TF tensor objects. So let's say you want to replace the features in any of these graph piece data, you can use this replace features API. Here we replace only the node-sats graph piece, while the contacts and AdStat data will remain unchanged. And now, different from contacts and node-sats, right? Within the AdStats, we have this adjacency information to keep the directed edges node endpoints. Adjacency structure keep the directed edge information using a source and a target tensor. So these are integer tensors that keep the node index to the respective node set. In this code snippet, you can see how to access the node features from the adjacencies using the adjacency source tensor, which keeps an index into the node set's feature tensors. So firstly, we get the source tensor from the purchase AdStat, and then we access the features we want to access is in the user's node set under the hidden state. Under the hidden state feature, now we can use the source IDs to access the respective feature values using the TF gather up, passing it the source IDs and the node states. So now how can you run message passing operators so you can basically send data across the graph? TF-GNN supports this via two main operators. One is these are complementary operators, broadcast and pooling. Here's an example of a broadcast operation using the TF-GNN broadcast node to edges call, which sends the edge feature from the source nodes to the adjacent edges of the AdStat is friend. And this function takes a graph tensor and will return a tensor for us. Let's recall our graph. So the isFriend AdStat had two edges, and now we want to send the edge feature from source nodes to their respective incident edges. And here, users with name York and Yumiko is the source nodes, right, for these two edges in the isFriend relation. So the return tensor is the broadcasted messages for each edge of the configured AdStat. This tensor has the first dimension as 2, which will be the number of edges in the AdStat. And you can think of the output from the broadcast operations as another AdStat feature. There's additional broadcast operators in TF-GNN library as well, such as broadcast contacts to nodes and broadcast contacts to edges. And these functions broadcast messages from contacts to the nodes and edges in the graph respectively. Now that we have these messages broadcast to the edges, let's aggregate them. We apply the pool edges to node operator to aggregate the broadcasted messages from the edges to the nodes with the node tag TF-GNN target, which is the target tag as initialized here. You can see in the code, and here we use some pooling also to aggregate the broadcasted messages at the target endpoint of the isFriend AdStat. This operator also takes the graph tensor and returns a tensor. And recall that in the graph, there is 3 nodes, right, for the user's node set. So the return tensor from the pooling operator will have an entry for each of these nodes. Since the first node in the user's node set, which is with the name Sean, is a target of both edges in this friend relation, it receives the value 59, which is the sampling result of the values 32 and 27, while the 2 other nodes don't have an incident edge where they are the target endpoints, so they just receive value 0. And we also have accompanying pooling operators that we looked at from context to node and edges. And these are pooling operators that are available from nodes and edges to the graph context, which is TF-GNN pool nodes to context and TF-GNN pool edges to context operators. And here is a typical flow of stages while building a GNN model. You can start with generating your subgraph samples. These are your graph tensors, and you can generate subgraph samples using either our in-memory sampler or the batch sampler. Then you can transform the graph features using the pre-processing step, and in the meantime, generating the hidden state vectors, followed by several runs of graph transformations with your GNN model, and then a readout layer which will extract relevant features to feed into the loss function to optimize model weights. During a feature processing step, you can transform your features before feeding them into your graph. TF-GNN library supports this map features keras layer that accept callback functions to transform each individual graph piece, node set, edge set, and context. Each of these callback functions can use the keras functional API and depend on the input parameters to learn trainable weights. Here you can see an example for a callback to initialize the node sets. It applies a linear transformation for one of the features, and for another categorical feature, it learns an embedding, concatenates them, and returns the tensor back. So the return value from map features layer callback functions can be just a tensor or a dictionary of tensors. When the callback returns just a tensor value, it will be mapped to the feature named hidden state. This is the default feature name TF-GNN layers read from and write to. Now let's build a graph neural network using the keras sequential API. So here we will be applying GNN layers at each step to transform the graph tensors. A GNN layer receives a graph tensor as input and returns a transformed graph tensor as output. In the keras sequential API, right, each layer receives its input from the output of the preceding layer. So as also mentioned earlier, TF-GNN library comes with a models subdirectory, which has implementations of various standard GNN architectures. And in this example, we will be using the GCN and GATV2 convolutions. So our first layer here is a GCN convolution that will apply the GCN layer over the hidden states of the input graph tensor. And after the GCN layer, there is the GATV2 layer, which applies graph attention convolutions over the hidden states of the input graph, which is the output of the previous GCN layer. Here you can add as many GNN layers as you want to declare your model. And after the training completes, now you will need to pick the relevant features from the graph, which is the readout layer, to make a prediction head. If your task is to classify each node in the graph, you can use tf-gnn.keras.layers.readout. This layer will be initialized with the node set name, and it will return the node states of each node for the specified node set. Now, if you have a graph level prediction task, you might want a graph level encoding, right? So how you do that is here you can, as you can see in this example, you can apply a pooling operator to aggregate the node states from the graph at the context level. And lastly, you can have a task to classify the root node, which is typically the central node for a subsampled graph. And calling this TF-GNN.keras.layers.readout first node will return a node state for the root node of the graph. And after each of these readout layers, you can apply a linear transformation to get the largest layer for your model. Here you can see examples for a binary classification problem where we apply a dense layer with size 1, with a dimension of 1. In this code snippet, you can see a Keras functional API model, which is used to build a graph neural network. Our input is the graph tensor. Then we preprocess and initialize its features, initialize the hidden state features, and then apply several runs of GNN updates to the graph. Then read out the relevant features from the graph to get the largest layer. Now that you have the largest layer, you can declare your model, build and compile that, declaring it with specifying optimizer laws and matrix values. And you can start the training loop with the model.fit function. So we have completed this slide.